Okay, here's a goodness of fit question. Okay, it's a goodness of fit question because we've got some observed frequencies. These are how many accidents there were for 100 days. And we want to see whether a Poisson distribution is a good fit. Okay, so the method is based on having some observed frequencies. Here they are. And we need to set up some expected frequencies to compare them with. Okay, so your first thing, or you can state your hypotheses. Okay, so your stated hypotheses, it says examine whether or not a Poisson distribution is a suitable model. So that gives us a clue to the hypotheses. There are my hypotheses. The null hypothesis is always that the model is suitable. Okay, so if the observed frequencies are not too far away from the expected ones, we'll go with the model. But if they're too far away, then we'll have evidence that the model isn't correct. We'll have evidence for H1. Okay, all right. Now, so it's always non-directional. All right. It ends up being a one-tailed test because chi-squared tests, for goodness of it, are always one-tailed when we come to the critical value and the test statistic. But the situation is either we have a model that works or the model doesn't work. Okay. Sometimes we have to include in our null hypothesis some feature of the Poisson model, but this just says set up any Poisson model you like. Does it work? So I'm going to have to, in the next bit, set up a specific Poisson model that best would have the chance of fitting this data. Yeah. So an alternative one would say, would a Poisson with a mean of 1.5 fit the data? Well, it hasn't said that. It hasn't given me a mean. So in the next bit, working out the test statistic is a long process, well, a longish process, starting by finding expected frequencies, but that comes back for my test statistic. I need to start by setting up a distribution. So my distribution is obviously going to be a Poisson one. Okay, so X is going to twiddle a Poisson, but it's going to be a Poisson with mean lambda. Where do I get my lambda from? Well, I wasn't given a mean, so therefore I have to estimate it from the data. So we estimate lambda from our X bar. Okay, how do I get an X bar? Well, I've got frequency data. So I lob it on my calculator in statistics mode, 1 var. So here we go. On the menu, I do 6, and I choose option 1 var. And in my frequency table, I entered the number of accidents, 0 or 1 or 2 or 3 or 4 down here, and I put their frequencies in the other column. So I go across and I put in 44 and 29 and so on. And when I've put all of those in, I press option, of course, and I press 1 var statistics, option 3. And it tells me an X bar, okay, 1.09. Now, while I'm on this screen, if I look on the next one, I look at Sx, well, no, bottom of this one, S squared of X. The variance of this, 1.65, is not that close to 1.09. So back in S2, you'd have actually done that comparison. Does the mean look similar to the variance? Actually, they're a little way apart. So maybe this is looking like bad news. Maybe the Poisson model is not going to be a good fit. But that's not the method we're applying now. We're actually going to do a full-blown goodness of fit. So I'm just going to take that 1.09 as my mean. Okay, X bar is 1.09, so I'm going to use my distribution X bar. I'm going to say, okay, suppose that I had the distribution Poisson with a mean of 1.09. What would my frequencies look like next for that? Okay, well, we don't do frequencies first, we do probabilities first, and we move on to frequencies. So probabilities, so what I'm going to do is say 0, 1, 2. Now, with my categories, okay, I haven't got a problem yet, but you always need to check the extreme categories. Is there anything possible below 0? -1? No, minus values you can't get from a Poisson. But at the other end of the distribution, for the data, there weren't any observed days when there were more than 4 accidents, yeah? But there could have been 5 or 6 or 7 or 8. There's no limit to the number of accidents there could have been, okay? So although the data may not cover the full range of possible outcomes from your distribution, you've got to bear them all in mind. So my categories, yes, they're going to be 0, 1, 2, 3. But the last category is actually going to be 4 or more. Just because in my data there weren't any days with more than 4 accidents doesn't mean there could have been. If I don't do this, then I won't get a set of probabilities. That's what I'm going to do next. I'm not going to get a set of probabilities that add up to 1. And if my probabilities don't add up to 1, I'm in big trouble. Okay? All right, sorry, I've drawn that incompetently, but I think we'll be able to manage. So now I've got to use this model, okay, to find my probabilities of these things. Actually, I'm going to say probability of x equals, let's call these little x equals little x. I'm going to have that in my third column because I'm going to do what we always have done and actually use Poisson CD, which is cumulative probabilities, which is the probability of x being less than or equal to x. Okay? All right. Now you can go straight to this middle column, this column here, by doing Poisson PD, but up to this point in the course, we haven't done that a lot. So let's stick with Poisson CD. So I'm going to do that on my calculator. All right. So I've done everything I need to on this screen. So let's go back to menu, clear menu, and let's do 7 for distributions. Okay. Let's go to Poisson CD. I'm going to go to option 3. Okay. And I could do the normal one, 2 variable, but actually this is a good occasion to do option 1, which is list. Okay, this enables me to enter, you can see that I can enter several x values, and they're going to be 0 and 1 and 2 and 3 and well, I'm going to stop there, I think. So 0, 1, 2 and 3, I'm going to enter those. I'm going to press equals, and I'll have to put in my lambda as usual, which is 1.09. And now, instead of having to do 0, 1, 2 and 3 all separately, okay, it will tell me the Poisson CD values for all of those in one table. It'll take a little while to do it, well, not that long. So here are my values. Now these are not rounded properly. So if we take one here, can you see this one here is 0.7269, so it's 0.7027, okay, but what's shown on the actual screen is 0.7026. So you do actually have to move that highlight over the numbers to actually find out what they round to, correct to 4 significant figures. Okay, all right, so I'm going to enter these values, correct to 4 significant figures into my table. Okay, there they are. I've entered these values in the table. This last one I had to round to 0.9745, okay, 0.9750. Okay, so I haven't done that last category, and I haven't worked out the probabilities of x equaling that particular value. So actually, let's start with this column here. So the probability of being less than or equal to 0 is the same as the probability that it does equal 0. So that is 0.3362. That one's the same. But what you'd normally do here to get the probability of 1 is you do the diagram, wouldn't you? 0, 1, 2, 3, 4, and so on. And you do the probability of being up to 1 minus the probability of being 0. Okay, so you do a subtraction of this value minus this one. So I have to do this value minus this one. 0.7027 take away 0.3362 is 0.3665. I make that. So I've subtracted these two values, okay? And then for the next one, I'm going to do 0.9024 minus this one. So you might want to pause the video and see if you agree with the values I'm about to get. Okay, so if you did pause and you've got those values, great. You might want to check I've done the subtractions right. I think I have. Okay, this last category, 4 or more, okay? All right, now for this one, we have to say that whatever probability we haven't already had must be accounted for here. So I could add all of these up and take away from 1, but actually this value of everything up to 3, if I take that one away from 1, then I get the probability of 0.0250, and these, if you add those up, you should get 1. Okay, so we've now got the probabilities. We've adjusted the last category so that it includes everything from 4 or more, and these probabilities will add up to 1. So that's the first stage. In any goodness of fit, set up the probabilities, make sure your probabilities add up to 1. Now, a shorter way to get these probabilities, you could actually use Poisson PD. You could use that list mode, and then that makes this column of the table fairly easy to set up. That's something you may want to practice, all right? But we've got our probabilities. What we really want is to compare some expected frequencies with these observed frequencies. So expected frequencies, I now need to go from probabilities. So this is the probability of any one occasion of there being no accidents, okay? But now I need to scale up. How many would I expect if we're looking at 100 days? Well, 100 days with this probability on every day. What you do is you multiply your probability by the number of days. So the total of the frequencies It's 100. 44 plus 29 plus 9 plus 10 plus 8. Check it. It's 100. It's got to be. It tells you it's going to be. So we multiply these by the total of the frequencies, which is 100. So, of course, we're going to get 33.62. And, of course, we don't worry that that's not a whole number. That's fine. So we're going to get 36.65. We're going to get 19.97. We're going to get 7.26. And we're going to get 2.50. Okay? Now, we know that for a chi-square test, expected frequencies of less than 5 are bad, okay? We don't mind if we've got less than 5s in this table. Observed could be less than 5 all they want to. But an expected frequency of less than 5 means we have to pool. So we're going to pool these two. So these categories are going to become 3 or more. So my last category is now going to be 3 or more. And my expected frequency for that is going to be the total of these, which is 9.76. So I'm now down to 4 cells. I've got 33.62. So the number of cells is how many cells you end up with after pooling categories. And it's 4, 19.97. Okay, so I've got those 4 expected frequencies to compare with the observed frequencies for the same 4 cells. So looking at my observed, the first one's got a frequency of 44. So my O's are 44 and 29 and 9. But my last O, because I've merged these categories for 3 or more, this is now going to be 18. All right. So I've got expecteds observed. I've just about left myself room for the contribution to chi-squared. So the contribution column, okay, the contribution to chi-squared is what I get when I do observed minus expected squared over expected. There's never any Yates's correction for goodness of fit, you'll be glad to hear. So I have to do the observed minus the expected, square it, and divide by the expected. So for the first one, so here we go, 44 minus 33, that's observed minus expected divided by expected. Oh, the top is squared. Observed minus expected squared divided by expected. Press equals, and I get 3.204. But for the first one, I want to cash in for my method marks, so I'm going to show the method for the first one. After that, I'm probably not going to bother. So in this first column, I've showed my method, and I've shown my answer. That says 3.205. I've had to write it really small, okay? And now I'm going to write the answers for the next 3, and once I've shown my method, I'm going for the first one, I probably don't need to for the others, so I'm just going to fill them in. So for my second one, here I'm doing it properly on the calculator, 29 minus 36.65 squared, okay, 29, 36.65 squared divided by the expected, and I'm just going to get my answer. I'm just going to record the 1.597. There it is, and then I'm going to do observed and expected. I'm going to do the same calculation for the last 2 lines and get their contributions. So now I've got all my contributions to chi-squared, so if I total those up, my chi-squared value will be the total of these, and these add up to 17.8. Okay, a few more decimal places, but 3 significant figures for this, 1 decimal place is good enough. So I've got a chi-squared value of 17.8. So I've finally got my test statistic. Okay, so the process is, we need to find probabilities so we can get expected frequencies. To find the probabilities, because I want to use Poisson CD, I actually put in an extra column for my Poisson CD values so that I could easily do all the subtractions in one go to get the probabilities. The last category was fixed to make the probability add up to 1 because I had to adjust it, remember, to 4 or more instead of just being 4. Okay, because although there weren't any data that were more than 4, in the Poisson distribution, we can have any outcome of more than 4. So I have to include all the possible outcomes, not just the outcomes that happened in the observed data. And then I discovered later on that I had to pool these two because their expecteds totaled more than 5. And of course I got the expecteds from the probabilities by multiplying by the total frequency of 100. Okay? All right, and then we went through and compared with the expected with the observed using O minus E squared all over E and adding them up. So that's where my 17.8 came from. Right, now on to the critical value. So I've got a chi-squared distribution. I need to know the degrees of freedom for the chi-squared. Okay, so for my CV, okay, well, I need to know 2 things. Firstly, I need to know my 1% significance level. So it's 1%. So in the chi-squared table, here it is. Okay, remember the 1% for goodness of fit and contingency tables, we're only ever interested in high-end chi-squared values. So these are the ones that tell us the observed and the expecteds are a long way apart. So it's this bit in here I need to be my 1%. Okay, so I need to use a p-value, not of 0.01, but of 0.99. Okay, but then I need to know my degrees of freedom. But I do know that p equals 0.99, so I've written that down. What's my degrees of freedom? Well, my degrees of freedom is the number of cells. Okay, now the number of cells started life as being 0, 1, 2, 3, 4 or more. Okay, there were 5 cells. Okay, but I had to merge these two, so I'm now down to 4 cells. So it's 4 cells minus, how many constraints are there? Well, I always have one constraint because I'm going to make the total of my expected frequencies 100, just as the total of the observed was. So you add up your expecteds, they have to add up to 100 because these probabilities had to add up to 1 and you multiply by 100. So that's one constraint you always have. But the other constraint is I actually used something from the data. I've made my data have a mean of 1.09. Now that didn't come from my assumptions, that came from the data that I was given. So I've now got 2 constraints, one from assuming what the mean was and one from the one we always get, the total frequency being 100, the same as the observed ones was. So I've got a degrees of freedom of 2 and a p-value of 0.99. So that means my critical value is 0.99, 2 degrees of freedom is 9.210 is my critical value. So my CV equals 9.210 and my comparison is 17.8 is greater than 9.210. Okay, so my distribution looks like this. It's one-tailed. Okay, my 1% is here. Okay, and this critical value is 9.210. I can see that I'm in the shaded bit. I'm not in the big not sig bit. So I am significant, and therefore because it's significant I'm going to be rejecting H0. And because I'm rejecting H0, I'm saying I have evidence. I'm looking at what H1 is. I've got evidence for H1. H1 is that the Poisson model is not suitable for these data, but now I need to go into context. Okay, so I can't just say evidence that a Poisson model is not suitable. I have to say what it's not suitable for, which is for the number of accidents occurring on the days. So there's my conclusion in context. Okay, I'll just go back. Have I answered everything in this question? I've examined whether or not a Poisson model is suitable for accidents per day, and I've got a conclusion, and I did use that significance level, so I am done. Wasn't that fun?